Hey everyone, my name is Venelin, and in today's video I'm going to show you how you can build a penguin classifier using PyTorch. We are going to build a neural network that takes as input some features from penguins and try to classify their species. We're going to have a look at how you can use PyTorch to create a dataset from pandas. Then we're going to split this dataset into train and test subsets, why we need this. Finally, I'm going to show you how you can build a neural network with PyTorch, and by extending the NN module from PyTorch, I'm going to show you how you can visualize the neural network with TorchView and why and how you can use ReLU or activation functions with your neural networks. Let's get started. There is a completely free text version of this tutorial on mlexpert.io. It also includes a Jupyter notebook that you can run on Google Co-op, and you can just follow along if you like. Neural networks or artificial neural networks are inspired by the function and the structure of the human brain, and in many today applications of deep learning or machine learning, we can see neural networks use it into images, text, structured and unstructured data, time series, etc. Pretty much everything that you hear about artificial intelligence today is very much connected to what neural networks are. Neural networks contain neurons, and those neurons are structured or grouped into layers. In this example of a deep neural network by the Stanford University, you can see that we have an input layer with 3 neurons or 3 input features. Then we have 2 hidden layers, each with 4 neurons, and then an output layer which contains just a single neuron. So for example, this might be used in a prediction problem when you have some features for houses and then you're trying to predict their prices, because this will be just the answer for the price. And as an input, you might have something like the square feet, the location, and probably something like how many neighbors are around there, for example. This way of visualizing neural networks might be good for small examples like this one, but when we are going to build something that is useful in the real world, pretty much every model that you are going to use is going to be much larger compared to this. We will have much more layers and much more neurons. So even if this video, I'm going to show you something that is relatively larger than this, and I'm going to visualize it using a library called TorchView. So let's have a look at our neural network, or the neural network that we are going to build in this video. And this is the visualization from TorchView. As you can see, we have again an input. It is called input tensor. Then we have an output, and this time the first parameter we're going to ignore it because it's going to be the batch size, something that we are not going to be very much worried about. But the second parameter in here is going to be the number of inputs neurons, or the features. Then we have a hidden layer, or the first hidden layer, with 8 neurons. Then we have this thing called ReLU, which is actually not a layer, and I'm going to show you what it is in a bit. And then we have this second linear layer, which again is going to have 8 neurons. And for the output, we are going to have 3 neurons. So it's going to be a bit different compared to the example that I've shown you. So let's build this neural network in PyTorch. Here I have a brand new Google Co-op notebook, and I'm going to start by installing some dependencies. We're going to use PyTorch 2.0 and TorchView for visualization of the neural network that we are going to build. I'm going to start by upgrading pip just in case. Then I'm going to download or upgrade gdown, which we're going to use for downloading our dataset. Next, I'm going to install Torch 2.0, which was very recently released. And then I'm going to install TorchView. And at the current time, I'm going to use, I have to specify double equals, TorchView 0.26, and I'm going to run through this. And this took a lot of time, but something that we had to do. I'm going to restart the runtime, and I'm going to pretty much ignore the warnings, since I'm not going to use any of the dependencies like Torch Vision, Torch Text, or Torch Audio. If you are going to do that, though, you might want to install those dependencies as well. And just to make things clearer, I'm going to clear the output of this. So the first thing that I want to do is to download the data, and I'm going to use the gdown for that. And this data is on my Google Drive. It's called penguins.csv, and if you open it, this is pretty much the exact same dataset that we had in the previous video. Yeah, exactly the same thing. So we have 344 entries or examples of penguins, which is great. Next, I'm going to close this and continue with some of the imports. And to do that, I'm going to start by importing Torch, which is the library that we are going to use. Then from Torch, I'm going to import the neural network module, which is just NN. And from here, I'm going to also need pandas. And I'm going to import matplotlib. Then I'm going to import Seaborn, which is, let's say, a helper for making better visualizations. And from Torch view, I'm going to import drawgraph, which is going to be the way that we are going to visualize our neural network. The first thing that I'm doing here is doing matplotlib inline. This will make sure that all the visualizations are going to be rendered within the Google Colab notebook. And then I'm going to set a couple of options using Seaborn. First, I'm going to make the default fixed size or figure.fixed size larger, just to make our visualizations look a bit better. And this is the width and height in inches, I believe. Then I'm going to do the same thing for the DPI, and I'm going to set this to 100. This also is going to make our figures larger. And then I'm going to set a default style, which is going to be just white with a muted palette of the colors. And I'm going to upscale the font size, because by default it's going to be pretty small. The next thing that I want to do is to import NumPy. And I'm going to set 2 seeds for the random number generators in order to make this reproducible. First is going to be the one for NumPy, and you'll see why we are going to need that. And then I'm going to specify Torch manual seed to again the same value, 42 of course. So setting these random number generators to 42 might give you a better way to reproduce the results that you're seeing during this tutorial. So this is something that is really important when you try to reproduce the experiments that you're running. But this might not be actually enough. We are probably going to discuss reproducibility in another video, but this will do just for now. So the next thing that I want to do is to basically load the data, and I'm going to use pandas for that. I'm going to just read the CSV file of the penguins, and I'm going to remove everything that is NA, or let's say irregular value. So PD is not defined. I haven't run this. Yeah, probably. All right. So this is the data frame. that we have here. We have 333 rows. And if I look through the data, you can see that we have pretty much everything that we've seen in the CSV file. We have species, IWant, the view length, view depth, flipper length, body mass in grams, the sex, and probably the year in which the recording was made. So using all of this data, the purpose of this tutorial is to create a neural network that can pretty much predict what the species is when we are given some of the information from here. So let's have a look at the distribution of the species and how much each one of the examples or the species is represented. To do that, I'm going to just count the number of species, and we have just 3 different types of species. And as you can see, the chinstrap is very much underrepresented compared to the Gentoo or Adelie. I'm not sure if I'm pronouncing this correctly, but in order to have a better look at this, I'm going to specify that I want this to be represented in a bar chart. And this is where our setting up of the charts is playing a very good role. You can see that we have a very good chart here. And then this is exactly the same numbers, but represented into a chart. And you can now visually see that the chinstrap is pretty much close to as half of as many examples as the dominant species, you can see. So why this is important? Well, when you're trying to make a predictor or a classifier for this type of problem, you might end up with something that is, for example, just predicting everything as Adelie, and it might have a very good accuracy. Or it might predict just Adelie and Gentoo, and again, might have a very good accuracy. But then in the real world, this underrepresented class in the labels or the dataset, you might want to have an accurate prediction for this one as well, but your model might be good at just predicting those two because it haven't seen enough of examples in this one. Next, I'm going to split all of the available data into train and test subsets. This is done because when we are training our model with some of the data and then trying to evaluate it on the same data, we are going to get some evaluation that is based just on the data that the model has seen. What your model can do in such situations is to probably just memorize all of the examples if it has enough capacity or memory to do that, and then just reply or predict based on the memorization that it did. When you deploy such a model in the real world, you might get very different examples of data, and then your model might have not seen it and then create predictions or do predictions that are wildly inaccurate. So in order to combat this, we are going to split the train and test the dataset into train and test subsets, and then we can use the train set to just train the model and the test set to evaluate the model on data that the model have never seen. To do the splitting itself, we are going to use a function from skwarn, which is called train test split, and I'm going to import that here. skwarn model selection, import train test split. Hopefully this is correct. And I'm going to go down here, and then I'm going to basically take the data frame and split it using this function. And the first parameter is going to be the data frame itself. And then I'm going to specify a parameter called test size, which is going to be just 20% for the test size. This is pretty much standard, but you might write different values for different data sets that you have. And here I'm going to take a train set and a test set as a result. So these are pretty much again data frames, and yeah, I'm going to execute this. And if we look through the train set, This will be just exactly the same data frame, but you might see that the indexes are all shuffled, and this is something that you don't want to have. So I'm going to just train set reset index, and I'm going to do the same thing for the test set. And I'm going to check the shape of each subset. All right, so we have 266 examples for training and 67 for testing. This looks good, but recall that actually PyTorch doesn't understand what data frames are. So I'm going to create a function called createDataset. That takes as a parameter the data, which is going to be a data frame, and returns a tuple of tensors. And I'll have to import this tuple typing helper. So I'm going to go back to the top, and from typing, I'm going to import tuple. So this is the function definition, and in here I'm going to do some processing of the data frame and then return the features, which is going to be used for the model, and then I'm going to return also the predicted result or the label for this particular example. So to get the features, I'm going to create a features variable, and I'm going to create a tensor from the data. I'm going to take the following features: the bin length in millimeters, then the bill depth in millimeters again, then the flipper length again in millimeters, and then the body mass in grams. All right, so this will just take these particular columns from the data frame, and I need to convert this into a NumPy array. And I'm going to specify a type to be float. So let me show you what this does. So let's just take the train set, and I'm going to essentially get this. So if I do just that, this will essentially give us a subset of the columns from the data frame. And if I do to NumPy, this is going to return just this NumPy to the array for each feature. So this is what we are doing here, and then converting everything to a tensor. And then I am requiring the tensor to be of type float, just in case. And these are the features. And for the labels, I'm going to again create a tensor. And here, for the species, as you recall, we have these strings. And PyTorch doesn't understand strings. So what we are going to do is to create a feature or species map or labels map. I'm going to call this species map. And in here, for each of the species that we have, I'm going to return an integer. For Adeli, I'm going to return a 0. Then for Chinstrap, I'm going to return 1. And then for the Gentoo, I'm going to return 2. And then I'm going to use this map just to map the string values. And I'm going to specify this to be a type of torch long. because these are going to be just integers. And I'm going to return the features and the labels. All right, so this looks good. Let's try and use this function. I'm going to create train features and labels, and I'm going to call them xtrain and ytrain. And I'm going to create a data set from the train set. Let's run through this. So it says that we have something that is incorrect. Oh, yeah, this is lowercase t. Let's try this again. All right, it looks that it's working. And if I have a look at the shape, we can see that we have exactly the same number of rows within this tensor, but then we've reduced the number of features to 4. And we can slice through this and get probably the first 2 examples. Yeah. So this is the tensors for the 2 examples of penguins that we have. And let's do the same thing for the ytrain. And we can see that we have exactly the same number, but then we don't have any other dimensions, just because this is just a list or array. So it's one-dimensional. This looks very good. I'm going to basically do the same thing for the test set. And I'm going to check the shapes just in case. And this is a very good practice to do, just checking the shapes of everything that you are building thus far as tensors, just to make sure that until that point at least you have not made any mistakes, because if you mess up the dimensions, then you might have to do a lot more debugging and have a look at where exactly did you do that. So just intermediately printing some of the shapes or all of the shapes that you can might give you much better experience when working with PyTorch. Now that we have a dataset that is converted into tensors, we can continue with building our neural network using PyTorch. And the first thing that I'm going to do is to create a class that will represent the neural network in here. So I'm going to start by creating this class and call it a penguin classifier. And this class is going to extend from nn.module, which is this import that we did from Torch right here. And this is pretty much a utilities module which contains a lot of helpers for neural networks or building neural networks with PyTorch. And I'm going to just for now extend from this one. Then I'm going to create a constructor. And then I'm going to also specify this function which is called forward. And this function is pretty much an override over the NN module. It is a very special function because it is used when you train your model. And it takes, in our example, the features which are going to be passed by the model. And then we are going to do something with it. And then return a result or prediction from this model next to the trainer or anyone that is using the model itself. We are going to add some parameters in the constructor, and I'm going to pass the number of features, which is going to be this number right here, because we had 4 features in our example for each penguin. And then the number of classes. And this is going to be again an integer. This is going to be essentially the species of the penguin that we are looking through. And this is going to be 3 because we have 3 different types of species. And I'm going to start this implementation by calling the super constructor. Pretty standard. And then I'm going to create 2 linear layers, which are basically helpers again from PyTorch. This will basically represent the network that we had here. So this will be the first linear layer, which is getting 4 inputs from the features and then outputting 8 neurons. And then we'll have this ReLU, and then we'll have the next linear layer, which again takes 8 and returns the number of quassis that we have, which is 3. So let's build this into PyTorch. And I'm going to continue with creating the layers. This will going to be the first linear layer. And this is the PyTorch class that we're going to instantiate. It is called linear, just linear. And it takes number of features and output of features, then a bias device, something that we're not really interested in right now. So for the first layer, if you recall, let me just close this. If you recall, we have this 4, which is the number of features, and output a number of 8, which is going to be the number of neurons. So here I'm going to specify just the input as number of features and then 8. And I'm going to paste this and take the second linear layer. And if you recall, it takes 8 and then outputs 3. So I'm going to take 8 and output the number of quassis, which is going to be 3 in our example. Okay, so we have a constructor, and then we are going to use basically those linear layers into the next forward method. So in the forward, I'm going to first call self linear layer 1 and pass in the features. So this is how you call the linear layer. You're just invoking it like a function. But I'm going to wrap this around this torch.ReLU. And I'm going to show you what this does. This is basically an activation function. And this activation function is taking care of removing the linearity that the neural network is going to have if we don't use activation functions. And I'm going to explain why and show you why we need this in the next part. But just for now, we're going to use this. And then I'm just going to basically return the result from the next linear layer. And I'm going to pass in X. So we're passing the features here through the first layer, then through the ReLU, creating this variable called X. And then I'm passing the result through the second linear layer. Pretty standard implementation of a neural network, very simple. I hope that you understand what is happening here. If you don't, please leave a comment below. I'll be happy to explain a bit further, or just read through the text tutorial. And if we run this, I can create now an instance of this penguin classifier. Yeah, the autocomplete is not very helpful. That's all right, the penguin classifier. All right, so the number of features is going to be 4, or you can be clever and take the shape of the X from here, but I'm not going to do that. You might try it. And then the number of quassis is going to be essentially the number of elements into the species map, which is 3. Again, you can be a bit cleverer than me here and try to run this. All right, so now that we have the model, I'm just going to print it. And this is pretty much a representation of what the model is. We have these 2 linear layers, which take 4, outputs 3, takes 8 and outputs 3, 4 and 8, 8 and 3. All right, so this looks perfect. Let me just try to pass in some data and get the result. And this is pretty much how you invoke this model. So let's have a look at the result. Let's say the first two examples. And this is the predictions for the first and for the second examples in our trained data set. So for the first and the second penguin. And as you can see, these numbers are pretty much random. That's because the model hasn't been trained yet. So this is pretty much expected. You can see that we have this thing called gradient function, which is something that we're going to explore a bit in the next video. But just for now, let me show you how you can create the visualization using Torch view that I've created and shown you here. So let's use this function called drawGraph, which is again imported right here at the top from Torch view, which is a great library. Thanks to the developers, by the way. And yeah, in here we can pass in the model, then the input size, which is going to be 1 for batch size, which we are not going to use, and then the device is going to be just meta, and this is the graph. Let's just run this. All right, it looks like that is running, and to visualize the graph you are just going to call visual graph, and this is an output or PNG image of our model thus far. You can see that we have pretty much exactly the same thing, but I've exported this as a SVG compared to this PNG image. So I've promised you that I'm going to tell you a bit more about what this ReLU thing is and why we need it. So this is an activation function that main job is to break the linearity of the neural network. You want to do that because this will allow you to learn much more complex patterns compared to some of the standard or pretty much basic linear models that you might have heard, like linear regression or logistic regression, etc. This is pretty much one of the most powerful components that allow neural networks to learn those complex types of tasks. Let me show you how you can do this in PyTorch. Luckily for us, PyTorch implements a lot of the standard activation functions, and ReLU is one of the most popular ones. ReLU is short for Rectified Linear Unit, and in this case I'm going to start by showing you what a linear function is and compare that to a ReLU. So to do that, I'm going to use Torch linear space, which is going to create basically a linear space between -5 and 5, and this will input 100 points between this, -5 to 5, and then 100 points, and then I'm going to apply ReLU or torch.ReLU over this, and I'm going to plot this using matplotlib. I'm going to just plot the x values, which is going to be the linear function, and then I'm going to plot the same thing but with the ReLU. Let me just call this ReLU, and I'm going to label this to say ReLU, and this will be the label for the linear example. I want to show the legend here, and I want to show the result. So let's run through this code. Okay, so we have this linear function, which is basically this diagonal value, which is going from -5 to 5, and this is the blue line. And then we have this ReLU function, which basically from this you can see that the ReLU is identical to the linear function once we are at 0 and above. But if we are at 0 or below it, we are just sticking to this 0 value. So you can think of ReLU as a clipping value or a clipping function for negative values. So this example is pretty much standard when you look through some of the textbooks or some of the tutorials online of what ReLU is, and this is pretty much the definition of it. But if we want to have a look at how does this affect, for example, a linear layer from Torch, this might not give you the best intuition about it. So I'm going to continue with another example in which we are going to use the linear layer from Torch and have a look at the predictions with or without using the ReLU function on top of the linear layer. And to do that, I'm going to start by taking this vector and I'm going to use the same x values. And then I'm going to initialize a linear layer, which we already did in our neural network. And I'm going to specify that we want 100 inputs and 100 outputs. Let me just in features equal to 100 and out features again equal to 100. And I want this linear layer to not require gradient. And I'm going to do this inline. So this is going to be something that we are going to explore in the next video, in which I'm going to show you the training process of a neural network. But just for now, just use it as is. And then I'm going to pass in the x vector through the linear layer. And then I'm going to take the ReLU result from the linear layer. So we have pretty much the same thing as before. So I'm going to get this. But instead of specifying x, I'm going to specify the linear layer and the ReLU layer here. And I'm going to just plot this. Also, I would like for this to not use the plot but a scatter plot. So this will just give us the dots, not these lines of the predictions. Okay, so each dot is an example of those 100 dots that we have right here. And each of those are run through the linear layer and then through the ReLU layer right here. And one of the factors that ReLU is doing on top of the linear layer is, again, that is cutting off these negative values, as you can see right here. While the linear layer can have negative values in the predictions or the neurons or the weights, you can see that when applied to the ReLU layer, we have only positive values and zeros. So this is another way to look at what ReLU is doing when you're using it in your neural networks. So this is it for this video. In it, we saw how you can get a dataset and prepare it for classification task. We created some tensors and splitted the dataset into trace and test subsets. Then we talked about how you can use PyTorch to create your very first neural network. We've seen how you can visualize the neural network with Torch view. And then I've shown you why and how you can use ReLU in your neural networks to make them non-linear. In the next video, I'm going to show you how you can basically take this model, this neural network, train it, and try to get the model to predict the correct to classify the correct penguin species, given the features that we are giving it. Thanks for watching, guys. Please like, share, and subscribe, and I'll see you in the next one. Bye.